Hello, Math 3 students. Welcome back to another lesson. So this is 1.2. Of course, make sure you have either this note packet printed out or make sure that you have a notebook and graph paper ready. So first, we're going to go ahead and do the task. And that's actually all we're going to do in this video is the task. It's quite long. So it says, when people first learn to drive, they are often told that the faster they are driving, the longer it will take to stop. So when you're driving on the freeway, you should leave more space between your car and the car in front of you than when you are driving slowly through a neighborhood. Have you ever wondered about the relationship between how fast you are driving and how far you travel before you stop after hitting the brakes? Think about it for a minute. What factors do you think might make a difference in how far a car travels after hitting the brakes? So some factors I thought about might be speed. Let me change my color. It's going to depend on how fast you're going. Maybe the weight of the car. If the pavement's wet. I don't know if how many of you guys have driven yet. But when it is raining or when there's ice or snow, that definitely affects your braking distance. So I guess really weather. Another would be maybe the condition of the tires or the condition of the brakes. So those are some that I came up with. So now it says there has actually been quite a bit of experimental work done, mostly by police departments and insurance companies, to be able to mathematically model the relationship between the speed of a car and the braking distance. How far the car goes until it stops after the driver hits the brakes. Imagine your dream car. Maybe it's a Ferrari 550 Maranello. I think that's how you say that. A super fast Italian car. I drive a Hyundai, so I do not have anything quite that fancy. Experiments have shown that on smooth, dry roads, the relationship between the braking distance, d, and speed, s, is given by the function d of s equals 0.03 s squared. Speed is given in miles per hour and the distance in feet. How many feet should you leave between you and the car in front of you if you are driving the Ferrari at 55 miles per hour? So what they're doing here is they are giving you your speed. We know that our speed is 55. So what we're going to do is we have to plug that in. We're going to say, what is d of 55 equal to? So we're going to plug that in. We got 0.03. And we're going to plug in 55 for speed. We get that our distance. So actually take a second, make sure you can plug this into your calculator, especially as we go through these videos. I really hope that you guys do follow along and make sure you are plugging these things in correctly and that you can calculate them yourselves. So when you plug this in, you should get 90.75 feet. All right, so if you're going 55 miles an hour, it's going to take you 90.75 feet to stop. Next one. What distance should you keep between you and the car in front of you if you are driving at 100 miles per hour? So of course you want to make sure that you have enough distance to stop if the car in front of you suddenly stops. So we'll go ahead and plug in our speed. So we're going to say, what is d of 100? It's going to be 0.03, 100 squared. And when you plug that in, you should get that your distance is 300 feet. Now I did take question C out of there, so don't be alarmed that we just jumped to question D right there. All right, so for D it says it makes sense to a lot of people that if the car is moving at some speed and then goes twice as fast, the braking distance will be twice as fast. Is that true? Explain why or why not. So let's test this out. Let's say our speed was 25 miles per hour, and then we'll have a speed of 50 miles per hour. All right, when we plug in the 25, we'll say, okay, what's our distance? 0.03. When we plug in 25 miles per hour. For this one, I get 18.75. And then that would be in feet. For 50, when I plug that into the function, I end up getting 75 feet. So you can tell right off the bat that this hypothesis that if you're going twice as fast, you have twice the braking distance, that's not true. All right. Right. If we double this did not double. And let's talk about why that is. That's actually because the function 0.03 s squared is quadratic. All right. If you recall, a quadratic function looks like that, right? So in this case, the hypothesis is false. And really the reason for that is because this is a quadratic function, so it doesn't grow like that. All right. So now they said, go ahead and graph the relationship between distance and speed. All right. So they want our speed on the x-axis and our distance on the y-axis. How we know that? It's because speed is inside of the function. That means that that's our input. And the input is always on the x-axis. All right. So let's look back at some of the points that we got. One that we can kind of just plug in right away. Here we have our S and our D. We know that we would have 0, 0. If we plugged 0 into that function, we would have a 0, 0 point. And then we also, let's see, looking back, we have 25. And we know that that's 18.75. Then we have 55 from the front page. And when we plugged in 55, we got, oh, actually, you know what? Let's do the 50 from the back. That makes more sense. When we plug in the 50, we get 75. And then when we plug in 100, we get 300. So we need to graph this. This is, of course, where having graphing paper is really going to come in handy. So please make sure you go and get that graphing paper. All right, so we're going to go ahead and graph these points. So I'm going to go ahead and make my x-axis here. We've got 0. And I'm going to go 1, 2, 3, 4, 5, 25. 1, 2, 3, 4, 5, 50. 1, 2, 3, 4, 5, 70. 1, 2, 3, 4, 75. 1, 2, 3, 4, 5, 100. All right, and then we're gonna go ahead and make our y-axis. So I'll do every 2 lines, I'll go 30. So we'll go 30, 60, 90, 120, 150, 180, 210, 240, 270, and we'll go 300. All right, now we can plot our points. We've got our 0, 0, and we'll do 25 and 18, which would be right about there. 50 and 75, a little bit above the 60. And then we've got 100 and 300. All right. So you can definitely tell that when we graph this, we get that quadratic curve right there. All right, so for number 4, it says, according to the Ferrari company, the maximum speed of a car is about 217 miles per hour. Use this to describe the mathematical features of the relationship between braking distance and speed for the Ferrari modeled by D of S equals 0.03 s squared. So really what they're asking for here is just your domain and range. Okay, so they told you here that the maximum speed is 217. So our domain or our input can be anywhere between 0 and 217. Then our range, we need to figure out what our range is. Obviously our range can start at 0 You plug in 0, you get 0. But we need to figure out, well, what's the upper end of our range? So we're going to plug in the upper end of our domain, which is 217. And we get 1,412.67. So that would be the upper end of our range. All right. Next, it says, what if the driver of the Ferrari 550 was cruising along and suddenly hit the brakes to stop because she saw a cat in the road? She skidded to stop and fortunately missed the cat. When she got out of the car, she measured the skid marks left by the car and she knew that her braking distance was 31 feet. How fast was she going when she hit the brakes? So we know that its distance equals 0.03 speed squared. And in this case, they gave us distance, so we need to solve for the speed. Our distance was 31. And so first thing we want to do is we got to work on getting that s squared by itself. So we're going to divide by 0.03. And when we do that, we get s squared is equal to 1,033.33. And then we're going to take the square root. Now, usually when you take the square root, you got to do that plus minus. But we've already pointed out that the domain of this function has to be, domain and range both have to be greater than 0. So because of that, we don't have to do that plus minus in this case. So we end up with 32.15. And really, if you think about it, it makes sense because you don't want a negative miles per hour. That just doesn't make sense in the context of the problem. All right, so that would be our speed there. Next, it says, if she didn't see the cat until she was 15 feet away, what is the fastest speed she could be traveling before she hit the brakes if she wants to avoid hitting the cat? So let's go ahead. We're going to plug in our distance, which is 15 feet. Divide by 0.03. And we get s squared equals 500. Take our square root, and you get 22.36 miles per hour. Next question says, part of the job of police officers is to investigate traffic accidents to determine what caused the accident and which driver was at fault. They measure the braking distance using skid marks and calculate speed using the mathematical relationships just like we have here, although they often use different formulas to account for various factors such as road conditions. Let's go back to the Ferrari on a smooth, dry road since we know the relationship. Create a table that shows the speed of the car when traveling based upon the braking distance. All right, so let's go ahead. We'll put together a table. And we can kind of look back. We already have found the relationship for when we plug in, when we have a distance of 31, when we have a distance of 15. So we can definitely put that on our chart. So we'll say distance and speed. So of course this one is still 0, 0. And we just found out that for 15, it is 22.36. And of course we know that we can use the points that we calculated from before, right? There's still going to be that same relationship between distance and speed. So if we look back at that chart, we know that when our distance is, say, 75, our speed is going to be 50. So we could say 75, 50. 100, 57.74. And then, yep, so we're good on that. All right. And actually, you know what? Let's get one more point. We could plug in, let's say we plugged in 500 for distance. All right. If you go through and do the math on that one, you would get 129.10. All right. So for 7, it says, write an equation of the function s of d that gives the speed of the car when traveling for a given braking distance. So before we had d of s, now they want s of d, okay? So really what we have to do is we just have to essentially find the inverse. We have to solve for s, okay? So we started out with d equals 0.03 0.03s squared. And since we need to solve for s, we'll go ahead, divide by 0.03. So we get d divided by 0.03 equals s squared. And we're going to take our square root. So we get that s is going to equal root d all over 0.03. All right, so that's what that function would look like. Another way to word this would be like, what is the function, like solve for s in terms of d. All right. All right, so they want us to go ahead and graph this. So really, I'm just going to go ahead, I'm just going to copy paste my chart from up here. We're going to graph these points, okay? So let's see, I'll do 100. And then we'll go, so that's 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000. All right, so we got our x-axis, or in this case, it's really our d-axis. And then we'll go ahead and we'll do 1, 2, 3, 4, 5, 50. 1, 2, 3, 4, 5, 100. 1, 2, 3, 4, 5. 150, 1, 2, 3, 4, 5, 200. All right, so let's go ahead and graph these points. We got 0, 0. Now we have 15. That's kind of going to be a hard one to plot. We could do the 75 and 50, though. That's definitely doable. And then we've got 157, which is going to be right there. Just about. And then we have 500 and 129, which is going to be about right there. So really, if we draw this curve, this is what it ends up looking like. Okay. So this one says, what do you notice about the graph of s of d compared to the graph of d of s? What is the relationship between the functions d of s and s of d? Okay. So really, let's think about these two functions we just drew. Okay, that first one looked like this. So that was our d of s function. We know that that one looked like that, and s of d looked like that. Okay, so really, what's going on here is this original function that we had is actually being reflected over the line y equals x, or x equals y. So when you have functions that are inverses of each other, you can reflect them over the line y equals x, and that's how you would graph it. All right, so inverses are essentially reflections of each other. All right, we're almost there. Last one. Consider the function d of s equals 0.03s squared over the domain of all real numbers, not just the domain of this problem situation. How does the graph change from the graph of d of s in question number 3? All right, so what they're asking here is, if you think about the domain of this function, they told us that the domain was 0 and 217, right? Well, if you think about like a regular parabola, the domain, it should look like that. The domain would be all real numbers. All right? Or you could say negative infinity to positive infinity. So next it says, how does changing the domain of d of s change the graph of the inverse of d of s? All right, so before we only had half of our parabola, right? Now I'm going to go ahead and draw in the entire parabola. Now, if we wanted to draw the inverse of this function, ooh, that was a pretty bad parabola. Let's try that. It's a little bit better. If we were to draw the inverse, the part that we drew before looked like this, right? But now we have to draw the entire parabola. So this red part would be the inverse of that function if it had its true domain. Then they said, is the inverse of d of s a function? Justify your answer. Well, is this inverse a function? No, it's not, right? That's not going to pass that vertical line test. It fails. So, no. Fails. Vertical line test. So basically, we need to restrict the domain here. We have to say what the domain is, because if we don't, then the inverse isn't